Welcome. Today we will be diving into Pastel-HN, the architecture of a modern Hacker News client. This session is designed as a case study in evolutionary architecture, where we will analyze the technical journey and the underlying structural decisions that define this project. We will explore how modern development practices and an adaptable architectural approach come together to build a performant, user-centric experience.
The vision for Pastel Inc. is one where aesthetics meet performance. This native desktop application is designed specifically for power users, combining a unique cyberpunk pastel design system with an optimized keyboard-centric workflow. To achieve this, we focus on three primary pillars. First, for visuals, we utilize high-contrast pastel themes to ensure a comfortable and readable interface. Second, speed is paramount. We have engineered the application so that every interaction feels immediate, maintaining response times of less than 100 milliseconds. Finally, we provide native support for macOS, Windows, and Linux through the Tori 2.x framework, ensuring a high-performance experience across all major platforms.
In Phase 1, we encountered what we now call the over-engineering trap, documented as ADR0001 during our Zig and WASM experiment. Our initial hypothesis was that WebAssembly would be necessary to achieve the high performance required for JSON parsing and URL building. However, a complexity audit revealed the true cost of this approach. We ended up maintaining 180 lines in main.zig, 237 lines for JSON handling, and 95 lines for URL logic, creating a total maintenance burden of 827 lines and a 61 kilobyte binary. As the diagram illustrates, the pipeline required compiling Zig source into WASM and then generating TypeScript bindings before the data could reach the UI. This experiment served as a vital lesson in the significant architectural weight that premature optimization can add to a project. Let's examine the boundary cost fallacy, specifically why small 500-byte payloads often perform better in native JavaScript than in WebAssembly. While it is true that low-level languages like Zig can parse data much faster, clocking in here at just 0.05 milliseconds, the raw parsing speed does not tell the whole story. Our analysis shows that the cost of crossing the memory boundary between JavaScript and WASM is significant. You must account for the time spent copying the string into the WASM heap and then copying the resulting fields back out to the JS environment. When these steps are aggregated, the total overhead actually exceeds the actual computation time, making native JavaScript the more efficient choice for small-scale tasks. Let's examine the impact of a recent architectural correction centered on the power of deletion. We successfully removed 827 lines of Zig code, along with the associated build configurations and manual memory management required for WebAssembly. This complex setup was replaced by approximately 150 lines of native TypeScript within our API.ts file. The outcome is a unified, single language stack that allows our team to iterate much faster. As highlighted here, just 10 lines of native JavaScript were ultimately able to provide the same functionality, proving that reducing complexity is often the most effective path toward maintainability and performance. Moving into Phase 2, we encountered significant limitations that we have documented in ADR0002, titled The Limits of Pure TypeScript. While our initial approach using pure JavaScript was simple to implement, the architectural decision to tangle UI rendering with data fetching eventually led to a degraded user experience. We identified 4 critical pain points. First, blocked UI. The single-threaded nature of the event loop caused noticeable interface stutter during heavy operations. Second, we experienced amnesia, where relying on in-memory caching meant all state was lost upon every page reload. Third, fragility became an issue. Our error handling was restricted to basic try-catch blocks without any sophisticated retry logic. Finally, we suffered from blindness, as our debugging capabilities were almost entirely limited to console log statements. This ceiling necessitated a fundamental shift in our technical strategy. The architecture shift presented here represents a strategic separation of concerns between TypeScript and Rust. In the UI layer, we leverage TypeScript for what it does best, managing the DOM, handling themes, capturing keyboard events, and implementing performance-focused features like virtual scrolling. By moving core logic to the data layer written in Rust, we gain significant performance and reliability for tasks such as API client management, persistent caching, robust retry logic, and structured logging. These two layers communicate seamlessly through Tari IPC. The primary benefit of this transition is a significantly smaller main.ts file, ensuring that the front-end code remains focused exclusively on user interface concerns, while complex data operations are handled by a high-performance system language. The Rust advantage is defined by its ability to unlock unprecedented levels of concurrency and safety through a robust ecosystem of specialized tools. At the core of our asynchronous architecture is Tokio. As the premier async runtime for Rust, Tokio enables true parallelism by efficiently managing thousands of concurrent tasks with minimal overhead, providing the high-speed foundation necessary for modern network applications. For our networking needs, we rely on Request. This library simplifies complex HTTP interactions by handling connection pooling and automatic retries out of the box, ensuring that our external communications remain resilient even under challenging network conditions. Data integrity is managed through Serde, a high-performance framework for serialization and deserialization. By leveraging zero-copy techniques and Rust's strict type safety, Serde allows us to process data structures at peak efficiency while virtually eliminating common data-related runtime errors. Finally, we maintain deep visibility into our systems using tracing. Rather than relying on simple text logs, tracing provides structured logging with spans. This allows us to track the lifecycle of specific requests and events across the entire stack, providing the context necessary for sophisticated debugging and performance optimization. Our intelligent caching strategy is designed to strike a precise balance between data freshness and high-performance navigation. We have implemented a tiered time-to-live approach based on the volatility of different data types. For feeds, where updates are frequent, we cache story IDs for 2 minutes. Individual items, such as stories and comments, are held for 5 minutes, while relatively static user profiles are cached for 10 minutes. To power this, our tech stack utilizes Mocha for efficient in-memory caching, supplemented by SQLite or SLED to provide disk persistence. This architecture ensures that critical data survives application restarts, directly supporting our goal of making the user experience feel instant and seamless.
Resilience by design involves a fundamental shift from simple string-based error handling toward a model of structured robustness. We achieve this through 3 core pillars. First, we implement structured errors using the anyhow and this error libraries, which provide the full context and backtraces necessary for effective debugging and system health monitoring. Second, we have integrated robust retry logic. By utilizing exponential backoff, the application can handle transient network blips invisibly, ensuring a seamless user experience despite connectivity fluctuations. Finally, we employ background refresh patterns to prefetch content. This ensures that data is always ready for the user without ever blocking the main UI thread, maintaining a responsive and fluid interface.
The reader experience is at the core of our platform, powered by the integrated capabilities of Algolia and Firebase. To ensure a high-quality interaction, we have focused on 3 essential pillars. First, our search functionality, driven by Algolia, offers a fast and precise way to locate content with intuitive filters for both date and relevance. Next, we provide enriched user metadata, allowing readers to see valuable context such as karma scores, user bios, and contribution history directly within the interface. Finally, we have implemented threaded comments to organize community discussions into clear, readable hierarchies. By combining powerful search tools with deep social context and structured conversations, we deliver a seamless and engaging environment for our community. Keyboard-centric navigation is a core design principle of this interface, enabling users to operate the platform entirely without a mouse. To ensure a seamless and native feel, we have optimized the system for a response time of less than 100 milliseconds. Users can instantly switch between feeds using keys 1 through 5 or refresh their current view by pressing 6 or R. Vertical navigation is intuitively mapped to the J and K keys, while the Enter key allows for opening or expanding selected items. Furthermore, the C key provides a direct shortcut to focus on comments, facilitating a high-velocity workflow designed for maximum efficiency. The final technical stack is structured to prioritize performance and type safety across every layer. Starting with the front end, we are leveraging Vite and TypeScript, with virtual scrolling integrated to ensure smooth performance when handling large lists. Serving as the bridge between our front end and the native environment is Tori 2.0, which allows us to maintain a small footprint while providing deep system access. Our backend is built entirely in Rust, utilizing the Tokyo runtime for asynchronous processing, Request for external communications, and Serde for efficient data handling. This backend interacts directly with external APIs, specifically the Hacker News Firebase and Algolia services, to provide real-time data and search capabilities. Supporting the entire development lifecycle are Bun and Task, which optimize our runtime performance and simplify project automation. As we look toward our future roadmap, we must identify the specific technical milestones that justify a shift toward WebAssembly. Introducing complexity like WASM is not about following a trend. It is about solving tangible performance bottlenecks that emerge as an application scales. The first major threshold occurs when we reach a volume of over 10,000 items. At this scale, executing a full history search in pure JavaScript can begin to impact the user experience, making WASM a necessary optimization for maintaining near-instant results. The second milestone involves the implementation of sophisticated offline storage. By leveraging binary serialization, we can significantly reduce the overhead of data transfer and storage. However, this requires the computational efficiency of WASM to handle complex encoding and decoding processes without blocking the main thread. Finally, as we integrate more complex fuzzy search algorithms, the sheer number of calculations required makes low-level performance essential. Ultimately, complexity is not inherently bad, it simply requires the right use case to justify the overhead. These three pillars represent the points where that investment provides the highest return for our application's performance and scalability.
Pastel-HN is designed as a platform where aesthetics meet performance. Our repository is hosted on GitHub at the address displayed on this slide, and the project is fully open source under the MIT license. To explore the code or contribute to the project, please scan the code provided on the right.